Audio Jungle.
Good day, everyone. Welcome to BSCM Channel 21 that discuss histories and discoveries of the wonders of mathematics. And today, I am your host, Patrick John Panopio, together with my partners, Maricar Zamora and Gerald Oloya, to discuss something intriguing and something special today. So Gerald, take it over.
Thanks, Pat. Today we will going to discuss about the what-ifs. I know all of us have many what-ifs in our lives. What if the earth is flat? What if we came from dogs? Just kidding. Apart from that, what-ifs are the chances and possibilities of every single event that could happen anytime and anywhere. And that entails about the probability in mathematics. So, Maricar, tell us more about probability.
Thanks, Gerald. Probability is related to the English words probe, probation, prove, and approve. All of these words originally had the sense of testing or experimenting. Probability attempts to express the relative strength of testing of confidence we have that an event will occur. How surprised would be if that event will happen? How surprised would be if it did not happen? Because we do have different degrees of confidence in certain future events, quantitative concepts become applicable to the study of probability. And today, as the program flows, let us all travel with time and have our exclusive interview to the dearest mathematicians of probability.
Yes, I am Girolamo Cardano. I started mathematization of probability. Sum of 3 dices, that's my idea. At face value, there are same number of combinations that sum to 9 as those that sum to 10. For a 9, 621, 531, 522, 411, 432, 333, and 410, 631, 622, 541, 532, 442, and 433. Liber de Ludo, or Book of Gambling, was published about a year after my death. In this book, I introduced the idea of assigning a probability P between 0 and 1 to an event whose outcome is not certain. The principal application of this notion were in games of chance, where one might bet, for example, that a player could roll a 6 with one die given 3 chances.
A French nobleman, who also a gambler named Chevalier Demir, proposed to me about the problem of dividing the stakes in a game where one player has bet that a 6 will appear in 8 rows of a single die. But the game is terminated after 3 unsuccessful tries. But I wrote to Fermat that the player should be allowed to sell the throws one at a time.
To answer Pascal, my answer is expressed as follows. The 3 first throws having gained nothing for the player who holds the die, the total sum thus remaining at stake. He who holds the die and who agrees not to play his fourth throw should take 1/6 as his reward. And if he played 4 throws without finding the desired point, and if they agree that he shall not play the 5th time, he will, nevertheless, have 1/6 of the total for his share. Since the whole sum stays in the play, it not only follows from the theory, but it is indeed common sense that each throw should be equal value.
Yes, I'm Christian Huygens. I wrote a very influential book on optics, wrote a treatise on probability in 1657, I wrote on the reasoning in a dice game. It is consisted of 14 propositions and contains some of the results of Fermat and Pascal. I also consider that multinomial problems involving 3 or more players. I also elaborated the Cardano's idea of an estimate of the expectation. I consider 2 players A and B taking turns rolling a pair of dice, with A going first. Anytime A rolls a 6, A wins. Anytime B rolls a 7, B wins. What are the relative chances of winning? The answer to that question would determine the fair proportions of the stakes to be borne by the 2 players. I concluded correctly that the odds were 31:30 in favor of B. That is, A's probability of winning was 30:61 and B's probability was 31:61.
I know that there has a rumor about that I am a gambler, but I am not. I am just observing and analyze many games of chance and suggest modifications of them that would make them fair or zero-sum games. Evidence that support my argument that I am not a gambler is that I have many manuscripts and some of that is analyzed by some experts. And they say that my works is indeed important in field of probability. The game I analyze is called Twinkie Novi.
Yes, you're right. I'm James Bernoulli. I did Ars Conjectandi, or the Art of Conjecture, that published by my nephew named Nicolas A. Bernoulli. The Ars Conjectandi is famous for my statement of general rule for summing integral powers as well as for the first statement and proof of the law of the large of numbers. The first parts of the book contain an extensive treatment of the theory of probability, mostly based on earlier work of Huygens and others. The final section is entitled The Use and Application of the Preceding Doctrine in Civil, Moral, and Economic Matters. It is here the law of large number is stated, but despite the imposing little of the section, it is quite short. Evidently, I found it difficult actually to apply probability to civil, moral, and economic matters. Note that the book as published includes a Dietas on infinite series and a letter I wrote to a friend about probabilities in the game of tennis.
Well, Abraham Moibre is my name. I was jailed as a Protestant upon the revocation of Edict of Nantes in 1685. When I was released shortly thereafter, I fled to England. In London, I became a close friend of Sir Isaac Newton and the astronomer Edmund Halley. I was elected to the Royal Society of London in 1697. But as a mathematician, I never succeeded in securing a permanent position. However, I also work as a tutor and gambling insurance. Many people in dice and other games were included, some of which appeared in the Swiss mathematician called Bernoulli's Ars Conjectandi, the year of 1713, or the Conjectural Arts, which was published before my doctorate. But after my demensura, I derived the principles of probability from the mathematical expectation of events, just the reverse of present-day practice. My second important work on the probability was Miscellanea Analytica, the year of 1730, or the Analytical Miscellany. and I was the first to use the probability integral in which the integrand is the exponential of a negative quadratic. I originated Stirling's formula, incorrectly attributed to James Stirling, the year of 1692 to 1770 of England, which states that for a large number n factorial equals approximately, that is n factorial, a product of integers with values descending from n to 1 approximates the square root of 2 pi n times the exponential of n times n, the n power. In 1733, I used Stirling's formula to derive the normal frequency curve as an approximation of the binomial law. I was one of the first mathematicians to use complex numbers in trigonometry. The formula known by my name, cos x plus I sine x n equal cos n x plus I sine n x, was instrumental in bringing trigonometry out of the realm of geometry and into that of analysis.
I, Nicolas Bernoulli, who did the St. Petersburg's paradox. The classical St. Petersburg's paradox is discussed in terms of doubling strategies. It is claimed that what was originally thought of as paradox can hardly be considered as very surprising today, but viewed in terms of doubling strategies, we get some results that look paradoxical, at least to the practical-oriented investor.
Thank you so much, Mr. Nicolas Bernoulli. But before we proceed to another mathematician, let us all watch the reaction video of Mr. Ben Vincent of YouTube community about the reactions of many mathematicians about the St. Petersburg's paradox.
Over time, there have been a number of reactions and responses to St. Petersburg paradox to try to kind of solve this paradox, and in this video I'll briefly highlight just a couple of these. So Kramer apparently made the argument that, well, nobody has an infinite amount of money. There also isn't an infinite amount of goods. Even if you run out of money, well, let me give you all my food. You know, there is just not an infinite amount of money or goods in order to actually pay up if someone were to play the game and actually win an infinite amount of money. And so this critique of the St. Petersburg paradox is that the game is just not realistic. Another response was, well, this is maybe a silly game because no sensible person would actually offer this kind of game, because if you were faced with potentially an infinite loss, that would not necessarily be a sensible thing to do. And so that was another argument. Another argument as well is to basically say, well, every time you play the game, you know, you have a 50% chance of essentially receiving your reward and being bumped out of the game. And so what you have is an exponentially decaying probability of still being in the game after each coin flip. And so maybe it doesn't make much sense to consider extremely rare possibilities. So, you know, maybe I just don't want to consider the possibility that it's so small of having flipped a coin and got tails 30 times in a row. You know, this becomes a vanishingly small possibility. And so one argument was that you, in working out what the expected value of playing this game is, that you only consider up to 30 tails in this game. And so when you do that, it turns out that the expected payoff is only £15. So what I've done here is to just include, if you're interested in working this out for yourself, I've just included a one-line piece of Julia code And if you run this line, what it does is to work out the winnings if you play this game over 30 trials, and it comes out at £15. Now, this is much closer to what people actually are willing to pay. Still a slight overestimate, but you get the basic idea. So these are possible resolutions or possible answers that people have proposed over time to the St. Petersburg paradox.
I am Pierre Simon Laplace. I am known as an astronomer. I also developed a great deal of theoretical physics. The partial differential equation, satisfied harmonic function, is named after me. I also understood the importance of probabilistic methods in the analysis of data. In my theory analytic these probabilities, I proved that the distribution of the average of random observational errors that are uniformly distributed in an interval symmetric about 0 tends to the normal distribution as the number of observations increases. Except for using the letter C, where we are now using E to denote the base of natural logarithms. I had what you now call the central limit theorem for independent uniformly distributed random variables.
Yes, I'm Adrian Marie Legendary. I dealt with the problems that frequently results when observation meets theory. Theory prescribes a certain number of equations of a particular form to be satisfied by the observed quantities. These equations involve certain parameters that are not observed, but are to be determined by fitting observations to the theoretical model. Observations provides a larger number of empirical approximate solutions to these equations, and thus normally provides a number of equations far in excess of the number of parameters to be chosen.
I, Carl Friedrich Gauss, studied about least square techniques for the purpose of methods of determining. However, I don't publish any of my writings because I thought that my works is not important. For that, I published a paper on observational errors, in which I also discussed the most probable value of variables based on a number of observations of it. I can say that my discussions was much more modern in its notation than those that had gone before, and also much more difficult. I also showed how to estimate this parameter.
In addition, Mr. Carl Friedrich Gauss also showed how to estimate this parameter by using the inverse probability methods. This work brought the normal distribution into a standard form, and it is now often referred to as Gaussian distribution. Gaussian distribution or normal distribution is a bell-shaped curve, and it is assumed that during any measurement, values will follow a normal distribution with an equal number of measurements above and below the mean value. Truly, what a great work, Mr. Gauss. Thank you so much for bringing this such wonderful contributions in the field of probability and statistics. After all the exclusive interviews to the dearest mathematicians that we had a while ago, let us all know more about the philosophical issues that arise in the history of probability. To discuss about that, let us welcome the experts, historians, mathematicians, and professors in the Philippines.
The notions of chance and necessity have often played a role in philosophical speculation. In fact, most books on logic are kept in the philosophy section of libraries. Many of the mathematicians who have worked in this area have had a strong interest in philosophy and have speculated on what probability means. In so doing, they have come up against the same difficulties that confront natural philosophers when trying to explain how induction works. Like Pavlov dogs and Skinner pigeons, human beings tend to form expectations based on frequent but not necessarily invariable conjunctions of events and seem to find it very difficult to suspend judgment and live with no belief where there is no evidence.
Can philosophy offer us an assurance that proceeding by induction based on probability and statistics in any better than, say, divination? Are insurance companies acting on pure faith when they offer to bet us that we will survive long enough to pay them more money, counting the return on investment in life insurance premiums that they will pay out when we die? If probability is a subjective matter, is subjectivity the same as arbitrariness?
What is probability when applied to the physical world? Is it merely a matter of frequency of observation and consequently objective? Or do human beings have some innate faculty for assigning probabilities? For example, when we toss a coin twice, there are 4 distinguishable outcomes: head, 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 tail, tail, head, and tail, tail. Are these 4 equally likely? If one does not know the order of the tosses, only 3 possibilities can be distinguished: 2 heads, 2 tails, and 1 of each. Should those be regarded as equally likely? Or should we imagine that we do know the order and distinguish all 4 possibilities? Philosophers still argue over such matters. Simeon Denis Poisson seemed to having it both ways in his investigations into plausible of inferences, when he wrote that the probability of an event is the reason we have to believe that it has taken place, or that it will take place. And then, immediately followed up within this, the measure of probability of an event is the ratio of the number of cases favorable to that event to the total number of cases favorable or contrary.
In the first statement, he appeared to be defining probability as a subjective event, one's own personal reason, but then proceeded to make that reason an objective thing by assuming equal likelihood of outcomes. Without some restriction on the universe of discourse, these definitions are not very useful. We do not know, for example, whether our automobile will start tomorrow morning or not. But if the probability of its doing so, we really only have 50% because there are precisely 2 possible outcomes. Most of us would not better or bother rather to buy an automobile. Surely, Poisson was assuming some kind of symmetry that would allow the imagination to assign equal likelihoods to the outcomes and intending the theory to be applied only in those cases. Still, in the presence of ignorance of causes, equal probabilities seem to be a reasonable starting point. The law of entropy in thermodynamics, for example, can be deduced as a tendency for an isolated system to evolve to a state of maximum probability. And maximum probability means the maximum number or equality of equality likely states for each particle.
And that concludes our program about the history of probability.
Thank you so much to the great mathematician who contributed a lot in our history. We owe a lot from you.
But before the program ends, I want to thank all of the audiences and viewers. Once again, this is BSEM Channel 21 that discover histories and wonders of mathematics. Have a great day ahead!